Okay, everyone. Thank you, everyone, to everyone who's come back. Thanks, Shwan. Give us very good introduction and to the principles behind free body diagrams and hip and ankle free body diagrams drawings. He's going to continue now the next half an hour with more joints. And please keep your comments and questions coming. I just had to let you know, after this session, we will carry on a small Viva session for people who want to take a hot seat on, or people who just want to watch. But that will be after this next block. Okay, over.
Will be aimed at guys who are going to sit their February exams. We are repeating this for some of you guys, so it's worth giving you something else different as well. Okay.
Brilliant. Thank you, Shwan. Over to you.
Okay. Thank you for us. So we discussed hips, we discussed ankle. I showed you how you can class 1 levers are easiest ones to resolve, and I showed you how you can change an ankle to class 1 lever as well. There's another class 1 lever in the body. There's actually 2 more class 1 levers that you should know very well. Okay. The first one is the spine. Purposely going to a difficult one. Everyone tends to think that these difficult ones are really hard, but they're not. They're very straightforward, very easy, nothing to worry about. So for the spine, what I would do is I would draw 2 motion segments of the spine, essentially. This is 2 vertebrae. And the way I would describe this to the examiner, apart from talking about all my assumptions, which we discussed earlier on, I would say this person is leaning forward. Okay? So I appreciate that this drawing is not leaning forward, but it's just easier to draw it this way using this whiteboard. So imagine this person is leaning forward, and if the person is leaning forward, then what we have is the person's whole weight, and he's carrying a weight as well. Let's presume he's carrying a box with arms straight and leaning forward. So he's hanging down. So the whole weight of the body and the weight of the box all combined gives you a force of W. Just bear with me. W, just there. Okay? W. Okay? So what's counteracting this force? Remember, our center of gravity is, our center of rotation is the disc. Our interesting little disc. I'm drawing quite badly. As I said, I'm not used to this. There you are. That's your disc. Okay? So our center is the middle of that disc. So what's the forces that are going there? Are the paraspinal muscles. Okay? They are then creating a force in the opposite direction. And remember, we're assuming this patient is leaning. Okay? So and this force is F. So then we just do the same thing as we did everywhere else. This is a type 1, class 1 lever. So there's nothing really special about it. We'll just change the color to blue so you can see the moment arms. And I suspect all of you have already kind of worked out how to draw this. Perpendicular, just let me erase this, that's not too deep. And then this one is perpendicular again. Apologize. And remember, this is the mathematical symbol for perpendicular, okay? So even if you're not drawing perpendicular, if you draw that and say it's perpendicular, the examiners have to accept it because you're saying the moment arm is perpendicular to the direction of force, okay? So if we say this is D, the shortest one is D, and then just take that as a multiple of D. In this case, we say 3D. The reality is, in the real life, you're drawing something like 5 or 6D, but it's very hard to draw this on a small piece of paper. Then resolving our forces, we've got F by D equals 3DW. Cancel out your d's. F is equal to 3 times weight. In this case, weight includes the weight of what the person is carrying, okay? So what's our joint reaction force? So again, it's the same thing. It's a type 1 lever. All you need to do is just add these lines together. And then do an equal and opposite reaction force, okay? So once again, everyone agree that that is relatively parallel? And then just add another line down there. And then, of course, if these are the arrows, if this is W and this is F, and then you go from tip of arrow, you add the tail to the tip of the arrow to the tail of the first arrow. And that's our joint reaction force. Okay? Again, if you say this is 3D and this is 3W, apologize, 3W and this is W, you can presume that you can take a guesswork of joint reaction force being equal to 3.5 times weight. Now, please be aware, you should draw this really big in the exam, and don't use 3D as your number. It should be something around the line of 5 or 6D, because your body weight is actually very far away from your center of rotation when you're leaning forward, compared to your paraspinal muscles, the muscles that are your erector spinal and so on, okay? Does that make sense? So do draw your lines far bigger, but I'm just showing you, it's just a simple class 1 lever again, okay? The next one is some examiners asked about the weight of the head on the cervical spine and how it affects the T2, the C2. Okay, so once again, just simple diagrams, nothing fancy. Don't be a hero, don't do anything foolish. Just do a simple diagram. So circle for a head. Okay, I like to draw my circle like an egg to represent the skull. A simple rectangle for your spine, and say your center of gravity, your center of rotation, your fulcrum is just there. Okay, that's it. That's all it is. Okay, so once you've done that, you can then take your weight again. Okay. And then again, the muscles at the back of your neck. Okay. And once again, it's a class 1 lever, type 1 class 1 lever. So there's your two different forces. If that's D and that's D, then F D equals D W. Therefore, F is equal to the weight of the skull. Simple as that. Of course, again, you could make it 2D, as in the weight of the skull. Your patient is leaning forward, so therefore the weight is far more forward, so you make it 2D. You can say that in the exam if you wish to say that. Okay, so, and then now to calculate your joint reaction force here again, it's just add the F, vector F, to vector W. Okay, in this case, because we've decided that F and W are the same size, let's just redraw that as F and W. And then your joint reaction force is equal to 2W. Does that make sense? I hope everyone understands this. Okay. Again, if you do decide that you're leaning the head forward, and I would advise you to do that, make your W far more forward and say it's 2D as opposed to distance is 2 times D. Okay, so therefore you can then get F is equal to 2W. And then your joint reaction force will be F sorry, joint reaction force will be equal to 3W. Okay? You all, I'm sorry, I just want to make sure you all understand. When you're drawing vectors, when you're adding vectors, you add them in the way you would add a parallelogram. Okay? So instead of, but what we're doing is we're taking a little cheat. Instead of doing parallelograms, we're doing triangles. Just to show you what I mean, if I take a line and draw it like that, take another line and draw it like that, and I want to resolve the forces on this point here. These are two forces. If I want to resolve these two forces on this point here, I then draw a parallel line like this, there, which is the equivalent of X, and this is Y. And I draw another line parallel, which is Y. Okay, does that make sense? So this is X phantom, for want of a better way of saying it, and Y phantom. What we then have is the sum of these two vectors is in this direction. These two forces are working in this way, and you can appreciate it's quite a large vector. Magnitude is increased, as you can see, and also the force direction is increased. So what we're really doing here is we're just not including this part. All we're doing is a triangle. So we're adding this force, and then we're taking the next triangle and taking it, sorry, I didn't put myself enough room. So we're taking this force, adding another force this way. And because we want to talk about opposite and equal reactions, therefore the sum of these two forces must give you an opposite and equal reaction in this direction. Does that make sense? Okay, so you all understand how to add vectors in this way. Okay?
Okay. Shwan, while you're talking about this, I had a good question coming through. Just a bit more expansion on the hip free body diagram and a little bit more explanation from you on how using a stick affects the joint reaction forces. How is difference between using stick on one hand, on the, the affected side versus using it on the contralateral side, and how does this affect joint reaction forces? If you could briefly touch on that.
Let me just quickly draw the hip again. Okay. So if this is the person's weight, W, and we have abductors going here, F. If the patient is carrying a stick on the opposite side, that's the force of the stick, S. Okay? So then what happens here is, if you take the moment arm of those two forces, if you think about it, this is a seesaw. So if I draw you a seesaw, there you are, this is a seesaw. This is the abductor force doing this to this, and this is the weight of the person doing that, and this is the stick doing that. As you can see, the two forces that are working together is F and S. They're on the same side. They're trying to rotate the seesaw anti-clockwise. The only thing that's working clockwise is W, okay? So this is what we're essentially resolving here. We're resolving those forces. So if you imagine, if you take F as your force abductor and you add S to it, you don't need a lot of F. You don't need a lot of abductor force to counteract the effect of your body weight, because you have S helping you. Isn't that right? But if you have no S, if S is absent, then yes, you do need quite a large F. Sorry. You do need quite a large F. Now, I do appreciate that I've drawn the distances wrong, but I just wanted to show you the principle of a seesaw here, okay? That's what we call a type 1 lever. So if your type 1 lever is in balance, then all forces must be resolved in equal within, okay? If you put your stick on the opposite side, so if you have a stick here on this side instead, okay, let's call this S again. I appreciate I'm not drawing the vectors in the right size, but I just want you to be able to see them. So let's put that S on this seesaw here, And then you can see that S here wants to help the weight. So what's happening is S wants to change the seesaw direction to clockwise. It wants to flip the seesaw clockwise. And the only, with W, so they're working together, while F is the only force that's working anti-clockwise. So if this is all in balance, then F is equal to W plus S. Okay, because the reality is F minus S initially, and then you take over the S to the other side, and F is equal to, does that make sense? Okay, so you can appreciate that F here is working far more harder. Your abductors are working far more harder. And if your abductors are working far more harder, they're far larger magnitude of the vector. And if it's a far larger magnitude of the vector, you have to add W onto that. And of course, you've minused a bit of S away, and now you've got a far larger joint reaction force. I hope that explains it, why you need to stick on the opposite side.
Yes, Shwan, that explains it very well. Thank you. I had another question, Shwan. Different type of levers, the shoulder joint, and people want to hear from you. How would you draw a shoulder free body diagram?
Okay, so these are the other levers that we need to move on to. That's correct. Okay, so let's talk about the shoulder. All right, so we'll start with that one. Once again, let's draw our. Remember, we're not drawing anatomy, and you must talk about your assumptions when you're drawing. Okay, so the best thing to do with this is everyone thinks that they need to draw the shoulder down. The problem with that is then you've got more complex muscles active in that situation than you really need, and you're now finding it very hard to find out where the direction of your biggest muscle, your deltoid, is going, because you can appreciate your deltoid is now working as a 90-degree angle muscle, as opposed to if you put it up here, it's now working as a contraction muscle. Does that make sense? So the best thing to do is draw your shoulder parallel to the ground, or just close to parallel to the ground. So if we take a small oval to show the humeral head, draw a line for the humerus or the arm, and draw the semicircle to represent the glenoid. Now, that's all you need to draw for all of this. You just say that the arm is held out at almost parallel to the ground. Then you put the weight of the whole arm through the center of the arm. In this case, we'll put it very close to the edge so that you can see the difference. That's W. And then what you then now need to worry about is your deltoid. So your deltoid is a large force in this direction. Okay? Does that make sense? Can everyone appreciate that the deltoid is now working in that direction if you go through the cross section of the muscle? So now what we need to do is, so what type of lever is this? Is this a class 1 or a class 2 lever or a class 3 lever? Well, the weight is further away from the fulcrum than the force counteracting the weight. So the load is much further away than the force that's counteracting it. So therefore, this must be a class 3 lever. Okay? What you then do is resolve your moment arms. This find out where your moment arms are. So in this case, the moment arm for here is perpendicular to the force of the abductor. Everyone happy with that? And the moment arm for your weight of your arm is perpendicular to the direction of the weight of the gravity. Sorry, I don't know why that disappears. The weight of your arm, so perpendicular to the direction of the force, which is gravity, straight down. Okay, so if we call this D and take this line D and add it to the moment arm of W, what we say is that's probably around 4D, let's say, or 5D. Let's say 5D for the sake of argument. Okay, so force by D is equal to 5dW. So F is equal to 5 times the weight of the arm. I hope you all understand that. As you can see, that it's not that difficult. You just need to work your clockwise and your anti-clockwise directions. Okay? Then what you need to do is add your vectors and get your joint reaction force. So if that's F, we add the W to the F, which is in this direction. Remember, tip of the arrow, tail of W goes to the tip of the arrow of F. And then you connect the two. There you go. So that's our joint reaction force. This is the direction our joint reaction force goes. And we can make a guesstimate that since F is equal to 5W, and this is now losing a part of a W, we can say this is 4.5 W is the joint reaction force. And if you move that there, this is the direction of your joint reaction force. Okay. If you think about it, F is trying to shove the humerus into the glenoid. Okay. And if this is in equilibrium, there must be an equal and opposite reaction from the glenoid, and that is your joint reaction force.
Okay, that's brilliant, Shwan. Thank you very much. That's really excellent. Shwan, we have a few requests about the knee.
There is just one very pertinent question about this. Stefanos has asked, why am I taking 4.5? Okay, so this is a gross estimation. This is not saying that this is mathematically accurate in any way whatsoever, but it's a gross thing. So what I'm doing is, if I take this line here and just bring it back to there, if you imagine I'm pivoting that line, the line JRF back onto the F line, what you're then seeing is not all of the W is taken there. Do you see that? If I take this W, that's where it should end up there. So therefore, I'm saying it's about half of W. So the JRF is 4.5 times W. I hope that answers your question, Stefanos. So, sorry, Firas, where were you?
So I think that's excellent explanation. As you said, these numbers you could, this part of your assumptions here, and as long as you can justify this, you could put any numbers you want. We just had a few questions, Shwan, obviously about the knee joint, and people need to be clear that the knee joint is which joint we are talking about. Is it the actual knee joint or a patellofemoral joint? And I think people want to know about patellofemoral joint. Okay. It's very difficult joint, this one, and a lot of controversies around it. And I don't know if you could clarify a few things for us.
Sorry, thank you first. I never start the patellofemoral joint by talking about the patellofemoral joint, because you can't resolve for a patellofemoral joint unless you know the forces around the patellofemoral joint, which means you have to go much further than what we are describing here, okay? So it's always a trick question when they say to resolve, show me a free body diagram for the patellofemoral joint. Everyone starts drawing that. What then happens is that they get themselves stuck, because then people don't know what the number is for those forces. So the way to start that is to actually just talk about the joint reaction force around the knee, okay? So what we do is, if I draw the ground here, and I draw this, a person is in a crouching position, just about to sit down. This is his tibia. And this is his femur. Okay, so then what I then say is that this person's weight is going through just around, let me just change the color so you don't get mixed up with the colors. This person's weight is just about here. Okay, because remember, if they're crouching, they're leaning forward, so they're halfway over their femur. This person is now in equilibrium. He's crouching like this, okay? So right now, in this crouched position, this is W. So what is trying to keep the person straight up? It's not his hamstrings. It's not his Achilles tendon. It's not his tib band. It's his quadriceps. So his quadriceps are now in action. If you take a look at this, if this is the fulcrum, let me just draw a little oval so you can see where I'm putting the fulcrum, just there. If this is the fulcrum, W wants to go anti-clockwise, and the quadriceps are attached to the pelvis, and they we're presuming they are. We're just talking about the full muscle of the pelvis or at the top of the femur. What we were saying is that the sorry, apologize, just 1 second, let me get a line. What we're saying is this is the force of the quadriceps. Okay, that's the anti-clockwise force. So what type of lever is this? If the fulcrum is here, the weight is closer to the fulcrum, but the force is further away, or the load is closer to the fulcrum and the force is further away. It's like a wheelbarrow. It's a class 2 lever. Okay, so now you've created yourself a simple class 2 lever. We call this F. So now we need to resolve for this. So if we switch again to our blue to get our moment arms, that's our first moment arm, and this is our second moment arm. Forgive me if I'm drawing very small here. In the exam, as I said, draw very big. So if this is D, then this, let's say, is 4D. Okay, so F is our clockwise action. F multiplied by D is equal to W, which is our anti-clockwise action, multiplied by 4D. Take away our D's, F is equal to 4 times the body weight. So that's our force is equal to 4 times the body weight. Now we want to do joint reaction force on this. So if we take the joint reaction force here, what we then do is, let me just switch colors because this is getting more complicated. So I just want to make sure we're in the same colors. If we take F, everyone agree that that's just about the same line, and then we add W. Sorry. Our joint reaction force is in this direction. Okay, so F W and joint reaction force there. Okay. Now, if that's the joint reaction force, we then have JRF is equal to 4.5 times body weight. Now, what we then do with that is we switch to the kneecap. And if we draw the kneecap as an oval to represent the femoral condyle, apologize, let me change color again to red so that we can see what we're doing. This is quite complicated, so that's why I'm taking a little time to make sure you all understand this. So that's your femoral condyle. And what I'll do is I'll draw the kneecap freehand and draw it like this. Okay, so now we know that there's a force of quadriceps which is equal to 4W acting on this person, correct? Keeping the person alive, but there must be an equal and opposite reaction of 4W. Let's draw green again. In the opposite direction of F. Okay, so we'll call this F again. If this is in balance, there must be a straight, if this is in equilibrium, there must be an equal and opposite reaction to F, which is the patellar tendon, which is going straight down again. There must be an equal magnitude to F. Okay? We'll call it patellar tendon for now, but it's equal to F in magnitude because it's in balance. Now, if you want to resolve the joint reaction force here, is we have that, remember I showed you that principle of the parallelogram? So if I draw that as a parallelogram, and there's your joint reaction force, which you can appreciate it's smaller than F, so therefore, let's say it's 3.5 times the body weight, which is quite a significant amount to put through your kneecap. Hope that makes sense.
I think that's excellent, Shwan. Really, it's very complex joint, and you explained that very well. I think this patellofemoral joint is possibly the most difficult joint for them all, really. So I think that's very useful, and people can definitely listen to this recording later on to review. I think we are getting towards the end.
One more, if you don't mind, for us.
Okay. Yes. Shwan, we have another 2 or 3 minutes, Shwan.
Okay. So just very quickly, the finger, everyone, the elbow and the finger, they're both the same, by the way. Okay, I'll just draw them both parallel to you so you don't waste time. Okay, so if I say, first of all, let's draw the elbow one first. If this is my humerus, this is my ulnar. Let's draw the finger. The thing is, everyone tries to draw the finger like this and put a weight like that on it, but nobody walks with a weight on their finger like that. If you're carrying your shopping bag, you carry it like this, isn't that right? Okay, so why don't you draw your finger like that, which is then now, this is your phalanx, this is your proximal phalanx, and this is your middle phalanx, and your small phalanx. Again, this is now what I would call a class 3 lever, an inefficient lever, the most inefficient in the body. Okay, what we then do is we draw our forces for that. We have the biceps here. And in this case, we have the FES here. We have the weight here. And here we have the weight of not just the finger, but the bag they're carrying. Here you can say the person's carrying a weight in his hand as well. So that's W for hand, sorry. That's X for hand, and that's W for the weight of the arm. And you can say this person is carrying a bag, which the weight of the arm is negligible here. The weight of the phalanx is negligible, so we can call this W on its own. Okay, so if this is F and this is F, you can appreciate that all you need to do is resolve your clockwise and anti-clockwise forces. The F is equal, in this case, let's talk for this one. So if we call this D, switch colors again, sorry, very quickly. This distance is D, this perpendicular distance. And if this distance is then 5D, and this is another 4D on top of that, we can then say FD is equal to 6D W plus 4DX. Okay? If you want to make life much easier for your elbow, because this is what they say, patient is carrying a weight on the hand, then just get rid of this W and just say this is the weight of the whatever they're carrying and the weight of the arm altogether in one. And that makes your life much easier. But anyway, there you are. F is equal to 6W 4X. And the same here, F, this is D, we'll call this 4D. is equal to W for G to D's, and F now equal to 4W. Okay?
That's brilliant, Shwan.
There are
We have,
literally 3 levers in the body, and you can create the same 3 levers in any joint. Just
good,
keep
good.
watch out for them.
Excellent. Thank you very much, Shwan. We have to wrap up this session because it's about to, our time is about to finish here. Next session will be a hot seat Viva session. Priority will be given to the February candidates. Not everyone will have a chance to have a go, but some people can just watch and learn. Some people can have a go. Shwan will be asking some of the common questions and giving some feedback just to, you know, give you a little bit of practice. So I will end this session now, everyone, and I will send you another link for the Viva session. If you have any, you know, burning questions you want to ask, we'll let you ask during the Viva session. Thank you everyone who has joined so far, and I will post another link shortly.
Thank you,
Shwan.